For almost 100 years, this stretch of northern China was one of the darkest places on the map. Coal dust in the air, coal dust in the water, coal dust settling on laundry lines so thick that people gave up hanging white shirts outside. The mines here fed factories, power plants, and steel mills across half the country. And then, one day, the coal ran out. The pits were abandoned, the machinery was hauled away or left to rust. What remained was a wasteland of collapsed ground, poisoned soil, and open black craters that nothing would grow in. Everyone assumed it would stay that way forever, but roughly 2 decades later, that same land is covered in millions of trees. Not a symbolic little park with a plaque, an actual forest with birds, groundwater, and shade. Engineers who studied the site in the early days said it was biologically dead. So, how exactly did anyone bring it back? To understand what happened here, you have to understand what a century of coal mining actually does to a piece of land. Most people picture a mine as a hole in the ground. That is only the smallest part of it. Underneath these hills, there were hundreds of kilometers of tunnels, some of them stacked in layers like the floors of a building. Miners removed the coal and left the empty space behind. For a while, the rock above held. Then, slowly, over years and decades, the ceiling of those tunnels began to sag. The ground on the surface followed. Roads cracked, houses tilted. Entire villages developed a strange lean, as if the whole neighborhood had been built on a slow-moving wave. Engineers call this subsidence, and it is one of the ugliest inheritances of underground mining. You cannot see it happening on any given day. You only notice it when a wall splits or a well suddenly runs dry. Then there was the surface damage, which was far more obvious. Open pit sections had been carved directly into the hillsides, leaving vertical walls of exposed rock 40 and 50 meters tall. Next to them sat the spoil heaps. When you mine coal, you do not just pull out coal. You pull out enormous quantities of worthless rock, shale, and clay that were sitting on top of the seam. That material has to go somewhere, and for decades it went into artificial mountains right beside the pits. These heaps were not natural hills. They were unstable piles of loose, broken stone that shifted when it rained and slid downhill in heavy storms. Some of them caught fire. Coal waste contains enough leftover carbon that, when compressed and exposed to oxygen, it can smolder underground for years. Locals described walking past heaps that steamed in winter and smelled permanently of sulfur. Those burning heaps deserve their own mention, because putting them out was a separate engineering problem entirely. A coal waste fire does not behave like a normal fire. It burns slowly, deep inside the pile, sometimes several meters below the surface, fed by air seeping in through cracks. You cannot hose it down, because water runs off the outside and never reaches the burning core. The crews handled it the only way that reliably works. They dug the heaps apart in sections, exposed the smoldering material, spread it out until it cooled, and then rebuilt the pile in compacted layers with the air pathways sealed off. Some heaps had been quietly burning for more than a decade before anyone touched them. Every one of those had to be dealt with before a single seed went into the ground above it, because a fire under a forest is not a forest for very long. The water situation was worse. Mining requires constant pumping, because tunnels flood. For decades, pumps ran around the clock to keep the shafts dry, and all that water was dumped into surface streams. The problem is that water that has passed through coal seams is not clean water. It picks up sulfur compounds, and when sulfur meets air and moisture, it turns into acid. The streams around the mine ran a strange rusty orange color, and nothing lived in them. Meanwhile, the aquifer under the region had been drained so aggressively that wells in surrounding farming villages started coming up empty. So the mine managed to do two contradictory things at once. It flooded the surface with toxic water while draining the underground supply that farmers depended on. By the time the last shafts were sealed, the region was left with a landscape that looked genuinely post-apocalyptic. Roughly 80 square kilometers of it, bare rock, cracked earth, craters filled with black standing water. Soil, where any existed at all, was compacted so hard that a shovel bounced off it. The pH readings in some areas were acidic enough to burn plant roots on contact. Soil scientists who took the first samples reported almost no organic matter, no earthworms, no fungal networks, essentially none of the invisible living machinery that makes dirt into soil. It was ground-up rock with poison in it. And the surrounding population had a much more immediate problem than ecology. Tens of thousands of people had worked those mines. Their jobs vanished with the coal, so the obvious question is why anyone bothered. Abandoned mine land exists all over the world, and the standard approach is to fence it off, put up a warning sign, and let it sit for a century. Restoration is expensive, slow, and produces nothing you can sell. In this case, 3 separate pressures happened to line up at the same time. The first was dust. The bare spoil heaps produced enormous quantities of airborne particulate matter every time the wind picked up, and that dust was blowing straight into cities downwind. The second was safety. Subsidence was still active, and unstable slopes near populated areas were a genuine hazard. The third was land itself. In a country where flat, usable land near infrastructure is extremely valuable, having 80 square kilometers of dead ground sitting next to existing roads and rail lines was an enormous waste of a strategic asset. That last point is the one most people miss. This project was never framed purely as an environmental gesture. It was framed as reclaiming real estate. The land already had highways running to it, rail spurs, power lines, and a workforce living nearby. All of that infrastructure had been built for the mine and was now sitting idle. If the ground could be stabilized and made productive again, the region would recover something worth far more than the coal that came out of it. That economic logic is what unlocked the funding. Pure conservation projects struggle to find budgets. Land recovery projects with a return on investment do not. But wanting to plant a forest and being able to plant one are very different things. The first teams that came out to survey the site made an assessment that discouraged almost everyone. You could not simply bring in trees and put them in the ground. There was nothing for them to grow in. Roots need air pockets, moisture retention, nutrients, and a stable pH. The site offered none of these. Early trial plantings were done anyway, partly to see what would happen. The results were brutal. Survival rates in some test plots came in under 10%. Saplings that did take root grew a few centimeters and then stalled, yellowed, and died. The lesson was clear and expensive. Before you can grow a forest, you have to manufacture soil. That became the real engineering challenge of the entire project, and it is far more interesting than the tree planting itself. Step 1 was earth moving on a scale that is genuinely hard to picture. The spoil heaps had to be reshaped. Steep, unstable piles were flattened and terraced into gradual slopes that would not slide, cutting the angle down until gravity stopped being a threat. Fleets of excavators and bulldozers worked the heaps for years, moving tens of millions of cubic meters of waste rock. The open pits presented a different problem. Some were too deep and too large to fill, so the decision was made to convert them rather than erase them. Their walls were graded back, benched into steps, and in several cases, the pits themselves were deliberately allowed to flood and become lakes. Step 2 was the crust. Even a reshaped spoil heap is still broken rock, so the teams built a layered system, almost like constructing a road in reverse. At the bottom went coarse crushed material for drainage, because waterlogged roots rot as fast as dry ones die. Above that went a barrier layer of compacted clay in the worst zones, designed to seal off the acidic waste below so contaminated water could not wick upward into the root zone. Then came the growing medium itself. This was not trucked in topsoil, because there is not enough topsoil in the world to cover 80 square kilometers. Instead, it was manufactured on-site from whatever was available in bulk. Weathered mine waste that had already leached out its worst chemistry, river silt dredged from nearby waterways, agricultural straw and crop residue from surrounding farms, composted municipal green waste, livestock manure by the truckload, sewage sludge from treatment plants, processed and blended in. The chemistry had to be corrected as well. Acidic ground was treated with agricultural lime and powdered limestone, sometimes in repeated applications over several seasons, slowly walking the pH back toward neutral. Technicians took samples on a grid across the site and mapped the results, because the contamination was not uniform. 1 hectare might be nearly workable while the hectare beside it was a chemical disaster. Every zone got its own recipe. In the worst areas, the treatment layer had to be more than a meter deep. In gentler areas, 30 centimeters was enough. This is the part of the project that took the longest and cost the most, and it produced absolutely nothing visible. For years, the site looked like an enormous construction zone, because that is exactly what it was. Then came the biology, and this is where the project got genuinely clever. Manufactured soil is still dead soil. It has the right texture and roughly the right chemistry, but none of the living organisms that make real dirt function. So the teams seeded the ground with life. Mycorrhizal fungi were introduced deliberately, because these fungi form partnerships with tree roots, extending the root system's reach for water and nutrients enormously in exchange for sugars from the tree. On damaged land, trees with fungal partners survive at dramatically higher rates than trees without them. Nitrogen-fixing bacteria were introduced alongside them. Earthworms were physically transported in and released. It sounds almost quaint next to the bulldozers, but the worms were doing something no machine could replicate. They tunnel, they aerate, they drag organic matter downward, and they turn a layered artificial construction into something that behaves like ground. Before a single tree went in, the site was covered in grass and low shrubs. This was not decoration. Pioneer species were the second stage of soil manufacturing. Fast-growing grasses with dense, fibrous root systems were sown across the terraces to lock the surface in place and stop erosion. Legumes were planted heavily because they host nitrogen-fixing bacteria in their roots, essentially fertilizing the ground for free. Sea buckthorn was used widely, a tough, thorny shrub that tolerates poor soil, fixes nitrogen, holds slopes together, and produces edible berries as a bonus. Alfalfa, clover, and various hardy native grasses went in by the ton, spread in some places by hand, and in others by hydroseeding rigs that sprayed a slurry of seed, mulch, and binder across slopes too steep to walk on. These plants were allowed to grow, die, and decompose in place for 2 or 3 full cycles. Every generation added organic matter. Every root that rotted left behind a channel for air and water. Every dead stem became food for the microbial population that was slowly establishing itself. It is a slow, unglamorous process, and there was tremendous pressure to skip it and get to the trees. The teams that skipped it, in early trial areas, watched their saplings die. The teams that waited ended up with survival rates several times higher. That patience is arguably the single most important decision in the entire project. Only then did the trees go in, and even then the selection was ruthlessly practical. Nobody was trying to recreate some pristine ancient forest. The first waves were pioneer species chosen for toughness rather than beauty. Black locust was planted extensively because it grows fast, fixes nitrogen, tolerates terrible soil, and does not care much about drought. Various poplar and willow varieties went into the wetter zones and along the new lake edges because they drink enormous quantities of water and thrive in disturbed ground. Chinese pine and arborvitae were used on the drier rocky slopes where broadleaf trees would not survive. Elm, ash, and hardy varieties of maple were mixed in. Fruit and nut species including walnut, apricot, jujube, and persimmon were planted in the better zones, chosen specifically because they could eventually produce income. The planting itself was a logistics operation more than a horticultural one. Millions of saplings had to be grown in nurseries, transported, and put in the ground during narrow seasonal windows in spring and autumn. Crews worked in lines across terraces, digging pits that were often filled with a scoop of prepared planting soil and a dose of water-retaining polymer gel, a substance that holds many times its own weight in moisture and releases it slowly as roots dry the surrounding ground. In the driest sections, drip irrigation lines were laid across entire hillsides, because a young tree that survives its first 2 summers will usually survive permanently, and one that does not, will not. Water trucks ran routes through the site during dry spells for years, and it did not all work. This is the part that rarely makes it into the celebratory version of the story. Whole plantings failed. Some blocks were wiped out by a single bad drought year. Others died because contamination that testing had missed was still leaching up from below. In several areas, subsidence continued after planting, and the ground cracked open beneath established saplings, severing their roots. Some species that performed beautifully in trial plots collapsed when planted at scale, because 100 trees and 100,000 trees are not the same experiment. In a few zones, monoculture blocks of a single fast-growing species were hit by pest outbreaks that spread through them like fire through dry grass. Each failure forced a redesign. Mixed species planting replaced monoculture. Planting densities were adjusted. Some areas were written off entirely and left as grassland, which is a perfectly legitimate outcome that nobody wants to admit is a legitimate outcome. Keeping track of all this required its own system. Monitoring stations were installed across the site to log soil moisture, temperature, and groundwater depth, feeding data back continuously rather than waiting for someone to walk out with a clipboard. Satellite imagery was used to measure canopy cover year over year, which is a far more honest metric than counting how many saplings were planted, because planted and surviving are very different numbers. When a block started failing, the data usually showed it months before it became visible, which meant crews could get water or replacement plantings in before the whole section collapsed. Water was the constant problem underneath everything. You cannot maintain a forest on land where the water table has been destroyed. So a parallel engineering project ran alongside the planting, and in many ways it mattered more. Check dams were built across gullies to slow runoff and force water to sink into the ground instead of racing off the site. Contour trenches were dug along slopes, thousands of kilometers of them in total, each one a shallow ditch designed to catch rainfall and hold it long enough to infiltrate. Retention ponds were excavated at the low points. The flooded pits became reservoirs. Treatment wetlands were constructed at the outflow points, planted with reeds and rushes that absorb heavy metals and neutralize acidity as water passes through them slowly. Over time, this began to show up in the measurements. The acid drainage that had turned the streams orange declined as the water passing through the site was buffered by the limestone treatments and the new wetlands. Aquifer levels, monitored by wells drilled specifically to track them, stopped falling and slowly started to rise. That change was gradual and easy to overlook, but for the farming villages around the perimeter, it was the single most meaningful result of the entire project. Wells that had gone dry began producing again. That is not a photogenic achievement. It also does not appear in any drone footage. But it changed people's lives more directly than any tree did. Somewhere around year 8 to 10, the site crossed a threshold. This is a real and well-documented phenomenon in ecological restoration, and it is the moment everything shifts. Up to that point, the forest is entirely artificial. It survives because people water it, fertilize it, replace dead saplings, and fight pests. After the threshold, the system starts running itself. Canopy closes enough to shade the ground, which cuts evaporation, which retains moisture, which helps more plants survive, which drops more leaf litter, which builds more soil, which supports more life. Birds arrived on their own and began carrying seeds in from surrounding areas, planting species nobody had selected. Insect populations exploded. Small mammals moved in. Understory plants appeared spontaneously that had never been sown. The forest stopped being a project and started being an ecosystem. Measurements from the site over that period tell the story in numbers. Organic matter in the treated soil climbed from essentially zero to levels comparable with ordinary agricultural ground. Soil depth increased on its own as leaf litter decomposed year after year. Vegetation cover across the reclaimed area rose from near nothing to the high 80% range. Recorded plant species climbed from a handful of stubborn weeds into the hundreds. Bird species counts went from almost nothing to well over 100. Dust storm frequency in the immediate area dropped sharply, and the air quality monitoring stations downwind picked it up. None of these numbers are dramatic on their own. Stacked together over 2 decades, they describe a piece of land coming back from the dead. The economics turned out to be more interesting than anyone expected, and this is where the story stops being purely environmental. The reclaimed land was never intended to just sit there looking green. Sections of it were converted directly into farmland, once soil quality allowed it, producing grain and vegetables on ground that had been a spoil heap. Orchards planted in the better zones came into production and started generating actual revenue. Walnuts and apricots and jujubes sold into regional markets. Timber blocks of fast-growing poplar were established with harvest cycles built in from the start. Some of the flooded pits were stocked with fish. Grazing land was created on the gentler terraces. The photovoltaic industry moved in as well, because reclaimed mine land is flat, cleared, close to existing power infrastructure, and has essentially no competing use, which makes it close to ideal for large solar arrays. In several areas, solar panels were installed above ground that was simultaneously being used for shade-tolerant crops or grazing. Then there was tourism, which is the part that surprised the planners most. Former mine sites turned into parks, and people came. The flooded pits became lakes with walking paths around them. Old mine buildings and pieces of colossal excavation machinery were preserved deliberately as industrial heritage rather than scrapped, because it turns out that a rusting 100-ton dragline sitting at the edge of a forest is a genuinely compelling thing to look at. Museums were built on some sites explaining what the mine had been and what happened to it. Restaurants, guest houses, and small businesses appeared around the perimeter. And that fed back into the employment problem, which was the human core of the whole thing. Mine closures devastate communities because mining towns are single industry towns. When the shaft closes, there is no second employer. The reclamation project itself became a major employer for years, hiring former miners to run earth-moving equipment, plant trees, maintain irrigation, and monitor the site. Many of those people already knew the terrain better than any consultant. Afterward, the jobs that came out of the recovered land were different in character, spread across agriculture, forestry management, solar maintenance, tourism, and food service. They did not pay what mining paid, and it would be dishonest to pretend otherwise. But they existed, and in a town where the alternative was watching the working-age population leave permanently, that mattered enormously. It is worth being honest about the limits of what happened here, because the triumphant version of this story does the actual achievement a disservice. This is not the original ecosystem. The forest that stands on this land now is largely a constructed one, dominated by species chosen for hardiness and economic value rather than by whatever grew there before industrialization. Its biodiversity, while vastly better than bare rock, does not match a mature natural forest and probably never will within any human time frame. Contamination has been buried, capped, and buffered rather than removed, which means the containment systems have to hold, and they will need monitoring for a very long time. Subsidence in some areas has not fully stabilized. Certain zones were simply written off as unrecoverable, and the water demands of maintaining forest in a semi-arid region remain a legitimate, ongoing argument among specialists, some of whom think grassland would have been the more sustainable choice in several of these areas. There is a broader criticism, too, which deserves airing. Reclamation projects like this can function as a kind of accounting trick, letting the industry that caused the damage point at the recovery and treat the ledger as balanced. It is not balanced. The cost of restoring this land ran into the billions and took 20 years, and it still does not deliver what the untouched landscape delivered. The lesson is not that damage can be fixed. The lesson is that fixing damage is enormously more expensive and slower than not doing it. And anyone using these forests as an argument that heavy extraction is harmless has the conclusion exactly backwards. But with all of that said, something real happened here, and it is worth understanding why it worked when so many similar efforts elsewhere have not. The first reason is sequencing. The project treated soil construction as the actual work and tree planting as the final step, rather than the reverse. Almost every failed restoration project on Earth gets this backwards, planting trees into ground that cannot support them, and then wondering why they died. The second reason is timescale. Funding and management continued across 20 years, through multiple failed phases, without the plug being pulled when early results looked bad. Most restoration efforts die in year 3 when someone looks at the survival numbers. The third reason is that the project was designed to produce value. Farmland, orchards, timber, solar generation, and tourism gave the recovered land ongoing economic reasons to be maintained, rather than leaving it as a permanent cost line that some future budget committee would eventually cut. The fourth reason is scale of intervention. Nobody tried to nudge this land back to health gently. They rebuilt it from the rock upward, moving tens of millions of cubic meters of material, manufacturing soil by the hectare, and importing entire biological communities from fungi to earthworms. It was closer to civil engineering than to gardening. That approach is enormously expensive, and it is why this model is difficult to export to places without the same capacity to mobilize labor, machinery, and long-term financing. It is a genuine achievement, and also a genuinely uncomfortable one, because the honest version of the lesson is that reversing this kind of damage requires resources that most of the world simply does not have. Which brings us back to where we started. There are abandoned mines on every inhabited continent. Appalachia has them, Germany has them, and has done remarkable work on some. Poland, Australia, South Africa, Chile, Indonesia, all of them are sitting on land that was hollowed out, used up, and walked away from. Most of it is still fenced off and doing nothing, generating no value, leaking contaminated water, and blowing dust into whatever town happens to be downwind. The prevailing assumption has always been that this land is permanently finished. What happened in northern China is a fairly direct argument that the assumption is wrong. Expensive to disprove? Yes. Slow to disprove? Absolutely. But wrong. The most striking thing about the site now is how ordinary it looks. That is the whole point. There is no dramatic monument to the restoration, no obvious seam between what was destroyed and what was rebuilt. Just hills, covered in trees, water in the low ground, birds in the canopy, and paths where people walk on weekends. Somewhere under all of it, a meter or two down, there is still capped mine waste and sealed acid rock, and the ghost outline of a tunnel network that once ran for hundreds of kilometers. The forest is standing on top of the wound, not instead of it, but it is standing. 20 years is a long time in a person's life, and almost nothing in the life of a landscape. The trees planted at the beginning of this project are now mature enough to seed their own replacements. The soil that was manufactured in mixing operations is now deep enough that nobody could tell it from the real thing without a lab. The children of the miners who lost their jobs when the shafts closed are working in orchards and solar farms on ground their parents helped dig out. That is not a tidy ending, and it is not a full recovery. It is something more useful than either. It is proof that dead ground is a decision, not a permanent condition, and that the decision can be reversed if someone is willing to spend 20 years and an enormous amount of money doing it properly. The coal is gone, and it is not coming back. What replaced it took longer to build and will last far longer than the mine ever did. And every year, without anyone planting a thing, that forest gets a little larger on its own. If you found this one interesting, hit subscribe. Every week, we break down the engineering and infrastructure projects that quietly reshape entire regions. The kind of thing that never makes the headlines, but changes how millions of people live. There are more videos on screen right now if you want to keep going. So here is the question worth arguing about in the comments. Is spending billions in 20 years to bring one dead mine back to life actually worth it? Or would that money do more good somewhere else entirely? I genuinely go back and forth on this one. Tell me where you land.